visiting us from Harvard, and I'll tell us about deformations of superconformal field theory.
Thanks very much for the invitation. So what I'll tell you today is some work in progress with Thomas Dumitrescu, who's another postdoc at Harvard, and Ken Trilligan, who's at UC San Diego. So let's start with some general motivation. So there's a general picture of quantum field theory. Which we'd like to call the Wilsonian picture, where, so here I'll talk now about UV complete field theories. Where in the ultraviolet, we have some conformal field theory, and then there's an RG flow to some IR theory. So if you want to understand general quantum field theories, it's useful as a starting point to understand what goes up here and to understand RG flows. And so my talk today will be in that spirit. Now CFTs are constrained because they have more symmetry. So operators and states in a conformal field theory are in reps of a bigger group which is strictly bigger than the Poincare group. So it's useful as a starting point for understanding general field theories to study the special case of conformal field theories because we get to use this larger symmetry group. And today I'll talk about that. So what are we going to talk about? We're going to classify RG flows. Is going to be our general point of our general program. Now, if you just start with a bosonic conformal field theory, and this general setup that I've said here, what can you say about RG flows? So there are two classes. Very broadly speaking. So the first class is spontaneous breaking. Of conformal symmetry. So spontaneous breaking of conformal symmetry is driven by webs of fields. Okay? And you can tell that it's spontaneous because there's a Goldstone theorem. So the low energy action contains a dilaton this dilaton sigma is the Goldstone boson for spontaneous breaking of conformal invariance. So examples of this are familiar from many field theories like n=4 super Yang-Mills or other supersymmetric examples where there's a moduli space. So this is class 1. Now there's a second class of RG flows, which is explicit breaking. Now, this is driven by operators. So we change our action in the following general way. So here, what are all these symbols? So this is our change in our action, first order. This is a local operator. and delta is its scaling dimension. This mu here is some reference scale. And this is some coupling constant.
Excuse me, the usual question of whether conformal boosts are also broken by these two mechanisms. Can you comment on this? For example, if you have a wave, do you break only scaling variance or?
No, you break everything.
Everything.
You break down to
Conformal
point
boosts as
group.
well.
Yeah,
Okay.
you break down to point
And in
group.
this case, however, you seem to have emphasized scaling variance up there.
So, well, I have emphasized scale invariance, but just as a way of not listing all the other generators. So
But they will be broken.
they will be broken.
Okay,
Yes.
thank you.
Yeah. Yeah. So both of these in general break you from the conformal group down to Poincare. Okay. So these are two classes of RG flows that you could study, and they're very different in character. For example, in this one there's a dilaton, in this one there's not. And in this talk, I'm going to study this one. So this talk will be about this case. So I just bring this up to point out to you that there's something else that can be done, but I'm not going to study it.
You could still have the dilaton though, right? And still do this as an operator. Could you?
Yes, you could imagine you could imagine sort of mixing and matching, or having a flow that has multiple stages where you have a dilaton and then you add an operator and so forth. Well, I'm just going to start off just by saying that I'm going to only study these kind of deformations of
And no dilaton.
Yeah.
Okay.
Okay. So what can we say in general with just conformal invariance? Well, we can say things that are very well known. So let me just review those momentarily. So now that we're studying explicit breaking, there's a split into three cases. So the first case, these cases are distinguished by what is the scaling dimension of the operator that I put in Lagrangian. So if delta is greater than the space-time dimension d, this is space-time dimension, then this is an irrelevant deformation. That means that lambda goes to 0 in the infrared. So that has the effect of you tried to move away from your CFT, but in the end, when you do the flow, you just go back to the original place that you started. Okay. Now the other side is delta is less than d. These are relevant. And in this case, you have the opposite effect. Lambda goes to infinity in the infrared. So these are operators and deformations that get more and more important as you move along the flow. So examples of these are like mass terms. And then finally, there's the borderline case. Delta equals d, and these are marginal. And this means that the scale invariance, and more generally the whole conformal group invariance, is preserved at least to leading order in lambda. So, yes?
So in the relevant case, does lambda really go to infinity, or it becomes strong and then we can't use perturbation theory and we don't know where it goes?
Okay, yeah, I mean, well, when it's really relevant, I mean, there's a power law growth just from the classical dimension of the mass. So there's some kind of logs perhaps that are correcting it from loop corrections, but it's very natural to say that it just goes to infinity.
Right.
Yeah, I mean, just think about like the flow of the mass of a free scalar, right? That's really getting bigger. In this case, since it's borderline, the log corrections become leading. The one loop beta function becomes very important, and then you have to, in order to say whether at higher order it really preserves scale invariance or not. You have to do a calculation. It can go either way. In the special case where to all orders in lambda, the deformation preserves conformal invariance, you call these exactly marginal. And those are true coupling constants, like tau in N equals 4 superangles. It's an actual dimensionless number the field theory depends on. Okay, so these are the three basic cases that everyone knows about. And, well, without putting in any more structure in the problem, there's not much more you can say. This is the end. So you can say that any conformal field theory has some set of operators which are irrelevant, some set which are marginal, and some set which are relevant. And if I want to do an actual flow, that is get away from my UV starting point, I should take one of these two. But you can't classify them any further. There's no more structure. Okay, so what are we going to do?
And renormalizability issues are not relevant here.
So renormalizability is essentially this statement that you want to be on this side. You want to have this one or this one. So if you can imagine doing, so here I put like a deformation of the action, but you can imagine doing this procedure even if you don't have an original action principle for your theory. You just do conformal perturbation theory. And then you can ask, what is the structure of the divergences that I'll encounter in conformal perturbation theory? And in the case where it's irrelevant, then you encounter very bad divergences. But in the case where it's relevant or actually exactly marginal, then you encounter only the sorts of renormalizable divergences that can be removed by local counter term.
Is that really guaranteed in any dimension? Any Lagrangian field theory I can write down?
In conformal perturbation theory, yeah. So I mean, you can ask me about. I started with a CFT, so I started with a consistent solution to the OPE relations, and I start computing formally in perturbation theory in lambda the corrections to correlation functions. And then the divergences that I'll encounter, so what kind of divergences will I encounter? You know, I pull down powers of this interaction and I encounter divergences when operators collide. And I integrate over them. But because I started with a consistent CFT, I get to use the OPE when things collide. And in the case where it's relevant, there's a finite number of things that are going to appear in the OPE because this finite number of singular terms. So that's why you...
I was thinking more like, let's say Young-Mills in 5 dimension. That's not normalizable.
But that you didn't start with a CFT.
Ah.
Yeah. So I put in a big starting point. I said start with a consistent quantum field theory where all correlators make sense with scale invariant, with conformal invariance. So that's a big assumption. It's a big starting point. So I fixed the UV to be good at the beginning.
Okay.
We'll actually come back to Yang-Mills later. Okay, so good. So like I was saying before, with just with just the conformal group, this is as far as we go. The story stops. But in this talk, we're going to do two more things. So we're going to add supersymmetry. So by that I mean that the UV starting point is superconformal. And then we're going to classify all flows preserving supersymmetry. So let me comment a little bit on this idea. So first of all, saying you want to start with a superconformal field theory means that the range of dimensions of interest is bounded. So they're not superconformal field theories in arbitrarily high dimensions. They stop existing above dimension 6 for purely algebraic reasons. And then you can ask, what do I mean by this word classify? So here I mean deduce all constraints that follow just from symmetry.
How much food did you wish to preserve in this
Yeah, so let me finish this. So, indeed, there are lots of different choices for how many SUSIs and how much preserving. So we will do it for all choices. So you see, because the list is so short, there aren't so many cases to do. So we'll do it for any n when you have a choice of n, preserving any other n, and you can just work it out.
The flow during the flow you can break it down to a subset of SUSI, but endpoint could still be.
Endpoint could still be bigger. So I don't have a lot of control over when there is accidental enhancement. So even you might say that you could fully break supersymmetry with your UV deformation, and then in the infrared still end up with an IR SCFT. I will not comment on that at all because I cannot control it. So I'm gonna only consider flows that are manifestly supersymmetric. More questions? Okay, so before diving into the details, let me tell you what the results are. Okay, so let's see. I'll explain in more detail how this works a little bit. So let me just make a little table here. Okay, so here I'm making a table of space-time dimensions and amounts of supersymmetry if I need to specify. So this is D and N. So D is the space-time dimension, N is the amount of supersymmetry, and then in this column let me put relevant marginal. And so an X will mean does not have any relevant or marginal as appropriate deformations. Preserving supersymmetry, a check will mean does. So 3D n equals 2, for example, has both relevant and marginal deformations. Okay. N equals 3 has relevant but does not have marginal. 40 n equals 1 has both, again. N equals 2 also has both. In the cases where these checks exist, we can classify them very explicitly. We can give a detailed list of all the possibilities, and I'll do that in some cases later. 5D has relevant but no marginal. This is with minimal amounts of supersymmetry now in 5 and 6 dimensions. And 6D has neither. Yeah, so in each case, we have some non-existence results here, and then we have some classification results in the cases where operators exist.
So those relevant or marginal deformation you listed, whenever they exist, are they supposed to preserve exactly the same amount of n you've listed?
Yes, and for this kind
not
of
subset,
not the subset.
Okay.
The subset is a little more. You have to have many more columns.
Sure,
Yeah, so I don't want to.
okay.
Yeah, but for this table, it's just literally preserving the what's listed. More questions about the results?
And you don't consider n equals 2 and 5 because that's not superconformal.
Yeah, there's no n equals 2 in UV CFT in 5 dimensions. There's just the one with 8 plus 8 supersymmetry. 60 here, this result is for n equals 1, 1, 0. Of course, the 2, 0 is then a special case, but since there's already a non-existence result for 1, 0, you don't.
Is there n equal 2 to Simon theory?
Hmm?
N equal 2 to Simon theory.
In which dimension?
5 dimension.
N equals 2. There's no superconformal group with 16 plus 16 supersymmetry.
No, n equal 2 I mean 8 supercharges.
By n equals 2, so by n equals 2 now you mean the minimal amount of supersymmetry.
Yeah,
So there's people have different conventions. Yeah. So indeed, I mean the amount, the minimal amount, which I guess in your language is n equals 2. It's the thing that reduces to 4D n equals 2 in 4 dimensions, which is where that name comes from. So it has 8 non-conformal supersymmetries. And those exist. And what this result says is that they have no supersymmetric marginal deformations, but they do have supersymmetric relevant deformations. And we can give a complete list of what they are.
These statements, are they based on Lagrangian field theories in the back of your mind, or are they more
So the method that
operator-based?
yeah, so the method that I'm going to talk about, this would be a good transition. The method I'm going to talk about is completely abstract, using just superconformal representation theory. But these results conform with Lagrangian examples. So okay, so indeed, the method will be representation theory.
Can I refine your table maybe? An attempt to refine it.
Okay, go for
The
it.
5 and 6 case. I think in the case of 5D, you may want to put their maximal, n equals 2 SUSY in the sense of being maximal, not 1. Because that has superconformal group, as you
Yes,
pointed
yes,
out
yes,
earlier.
yes, yes, yes. I want the
So
one
I
that
would put
has.
n is 2.
Yeah, okay, and that.
N is 1 being minimal.
It's inconsistent with his other use of ends.
Is it?
So the minimal amount of supercharges for even for a non-conformal group in 5 dimensions is 8 total real supercharges. That's the minimal that it could be. 8
A
total.
conformal group.
So in this case, the only conformal group has 8 Q's and 8 S's.
So it's unique, that's why we didn't bother writing n value.
Yeah, yes.
Okay. What about 6? I can think of n is 1 and n is 2.
Yes, and so this
and
result.
Which one do you have in mind there?
This one is the minimal. This is 1, 0.
Ah, okay.
So then the 2, 0 case is a special case of this,
Uh-huh.
and it's still this result is still true.
Okay, thank you.
Yeah. Okay, so how do we proceed? Well, we need some method, especially if we're going to be studying 5 and 6 dimensional superconformal field theories. We need some method that's not Lagrangian based, because there's no Lagrangian examples of 5 and 6D superconformal field theories, even though we believe they exist from various string theory realizations. So we need some method that doesn't rely on Lagrangians. So the method is this representation theory. So what we know in general is that operators are organized into unitary reps of the superconformal group. Well, okay, so what that means is that you have some representations of the conformal group that I was talking about below, labeled by scaling, or earlier taught, labeled by scaling dimensions, and that they're connected by various actions of Q's. That's all that really means. And there are some relations that you get on the quantum numbers of these operators by this connection. And, well, what does it mean for the deformation to preserve supersymmetry? We have delta S, which I wrote schematically like this. Let me leave out some of the other stuff that I wrote there for a minute. So supersymmetry means Q on this delta S is 0, which is true if and only if Q on O is a total derivative. So you see, this is a statement that can be checked using just the supersymmetry transformation of O. So this is a statement that can be phrased just in terms of the representation theory of the superconformal group. So we can go in now and look for operators O that are in representations that have this property, where you act on them with Q's and you get total derivatives. Yes?
Should I assume some appropriate fall-off conditions for V?
should you assume some appropriate fall-off conditions from D?
Action can still change.
Well, we get our results without having to assume them. You might say that there could be something stronger, but all the results, all the cases that we find exact actual Lagrangian examples of everything where there's a check without imposing any additional constraints. Okay. So coming back to this, the basic crux is that, well, there's this method of representation theory, and all representations are actually known.
These are representations of SOD, 2.
No, the superconformal group. The
Superconformal version. Okay.
Yeah, the super enlargement. Of
Yeah. I mean, when you say unitary by itself, is that sufficient? Because there could be discrete unitary, there could be some other.
No, there are lots of different unitary representations. I mean,
Will any one of them do for you?
Any unitary representation with the highest weight state is an allowed.
Highest weight.
Yeah, it has to be a highest weight representation. Yeah. Highest weight. Yeah.
Lowest weight doesn't work for you.
Okay, maybe I'm switching what I mean by lowest and
Yeah.
highest.
But
Sorry,
there's-
probably I mean lowest.
You mean lowest weight, probably.
Yeah.
There's one odd case out, I must mention this, sorry. SO2, 2 case in 3 dimensions. It's the only case where the group is reducible. You have SO2, 1 cross SO2, 1 product. That happens only in 3D. 2D, sorry, 2D.
Yeah.
In that case, am I sure that on both sides of those factor groups, I must have lowest or highest weight on each side, or can I mix them?
You have to have on both sides this property because if you act with the lowering generator and you would never annihilated you would encounter something whose scaling dimension was unbounded below. So you would
reject those.
Yeah, I mean I want the radial Hamiltonian, the radially quantized Hamiltonian, to have a positive energy spectrum. So I want the theory, if you quantize it on a circle, to have a positive energy spectrum.
So you insist that both factor groups should have lowest weight representation.
Yeah. No, okay. Of course, in
Or highest,
2D,
but
yeah.
you don't mix.
Yeah. In 2D, you can. There are more general versions of conformal field theory where you could relax this, but I'm putting in right now the strongest assumptions that I can
Okay.
to see what I get.
Okay.
Okay. So all representations are known. By that I mean all representations of this type are known. So given that, it's just a finite amount of work to list them all and investigate which of them have operators O that can satisfy this condition. So that's what we're going to do. Any questions about this? Very simple idea. Could have probably been done many years ago. And certain special cases were done years ago. For example, 40 n equals 1 has been known for quite a while. I didn't even list 2D up here, even though we've done that also, just because everything in 2 dimensions was done quite a while ago by many other people. And the real new stuff from what we're doing are the 3D, 5D, and 6D cases. That's where most of our new results are.
You mean 2 and 4 are to be avoided because it's jungle, basically?
No, I mean we're happy to do them, and the same methods work. I just mean that people have sort of already done lots of bits and pieces of it. So okay, we summarize those results in our upcoming work, but you know there's also 1,000 references there. Question?
This might be something. So in the case of non-Lagrangian theories, does it make sense to talk about the change of like the?
Yeah. So that's what I was alluding to before in the case of by conformal perturbation theory. So
Okay.
imagine your CFT, your abstract CFT, is just a list of operators and a list of their correlation functions. Okay, so now I want to know what does it mean to have this delta S in that case. So if I want to compute O1 of x, On of x, n in the deformed theory lambda, I'm instructed to try to compute this thing that I was writing here, and then O1 of x1 and lambda equals 0. So this is something that's defined purely in the CFT, and this is something that at least can be computed order by order in lambda. Non-perturbatively, it may be hard to define what you mean, but at least order by order, it's the same as doing usual Feynman perturbation theory. Yeah, okay, so let's do a detailed example so that you see how concrete this can be made. I'll do 3D. I'll explain why I do choose this one. So what's the superconformal algebra? It's this OSP n/2. So there's some real form of this. I won't specify the real bit. But it's the real form of this. So there's a bosonic subgroup here, which is SON times SU2. And so this here is the R symmetry. And this is the Lorentz symmetry, Euclidean rotation. Okay, how do we label local operators? So they have a collection of quantum numbers, which I'll now enumerate. So the first is this scaling dimension that I wrote before. Delta is a non-negative real number. Sorry, in R. Okay, that's easy. Then there's a representation of SU2 that I wrote there. And in my conventions, which some people may find perverse, I'll label them by a non-negative integer, j, and the dimension of this rep labeled by j is equal to j plus 1.
By the way, when you say SU2 Euclidean rotation, you are still in Lorentzian signature, but what you mean by that is the SU2 complex subgroup of SO3, 2, correct?
Well, actually, I'm imagining, so to do the representations for operators, I'm imagining doing a Wick rotation. So I'm imagining that I'm quantizing my theory on a sphere.
So you're Euclideanizing the theory.
Yeah.
But still, this SU2 is present in both cases.
It's present in both
It's
cases.
a rotation subgroup of the conformal group.
Yeah.
In both cases. Okay.
Yeah. Its quantum numbers are the same. Yeah.
Okay.
Okay, so we've got this scaling dimension, we've got this integer spin. Okay, we've got more because we've got this R symmetry, so of course things will be the representation of the R symmetry. So there's some representation of this SON. Now, okay, it's easy enough to work with representations of SON, but since I'm going to do some real-time calculations, let me, for simplicity, in the example, I'll take n is 3. Then this becomes SO3, which has the same labeling scheme as up here. So we'll label by an integer r, which has a similar feature to this guy. So that's just for simplicity. Of course, in general, you can do representations of SON. I just don't want to do them on the board. Okay. So what is the structure of a general representation?
Is n is 3 equivalent to n is 4?
No. In 3 dimensions it's not. Yeah.
In 4 it is.
In 4 it is, yeah.
Not in 3.
And not in 3. In 3 dimensions there are real CFTs that are n equals 3 and not n equals 4. Yeah. Yeah, there's a whole zoo. In fact, these kind of methods can be used to understood that kind of issue as well. And I'll tell you about that afterwards. Okay, so what is the structure of a representation? So, so the structure of representation is probably familiar. So there's some O which I'll call the primary. This is an operator, and it's got the smallest delta. Then you hit it with Q, and you get some new O prime. Now this guy has delta equal to delta of O at the bottom plus 1/2, because the Q's carry space-time dimension 1/2. Anyway, you continue this game until you get to the top. Like this. Okay, so it's useful, so this is a general representation. So all of these operators, of course, have quantum numbers, like I've listed here, but we can label this whole multiplet by the quantum numbers of the bottom. So this is the convention. So we label such a multiplet. So we choose to label things by the quantum numbers of the primary. Okay, so speed up a little bit. So what are the operators? I told you that all the representations are known, so let me just tell you what they all are. Okay, so list of representations. So okay, so the first kind of representation is what I'll call L. L means long. So what are its properties? So it satisfies the constraint that delta is greater than or equal to 1/2 J plus R plus 1. And it has no null state. What is a null state? So a null state is some non-trivial combination of Q's which annihilates the primary. So there's some, this chain here is always of some finite length. The general length is equal to the total number of Q's that you have. But there can be special multiplets where it's shorter, because some number of Q's, some non-trivial combination of Q's, kills the bottom guy. So this long multiplet L that I wrote there is a representation that satisfies this properties on its quantum numbers, and it has no combination of Q's that kill it. Okay. Then there's a thing that's called A1. This has delta equals 1/2 J plus R plus 1, and J is not equal to 0. All right, now there are going to be some null states. So to write them, I'm going to have to tell you a little bit more about the supercharges. So what are the representations of the Q's? So they have J equals 1, R equals 2, delta equals 1/2. So I'll write them as Q alpha I J. So this here is a SU2 J doublet index, and these here are SO3 R doublet indices. Okay. So now that I've told you what the Q's are, I can tell you what the null state, say, of this guy is. What does it look like?
Is this symmetric in INJ?
Yes, yes. Right. So my in general, if I have left things off, everything that I write will always be symmetric. But yes, this is symmetric in IJ. The Q's are in a vector representation of the R symmetry in 3 dimensions. So this is a null state. So So you have some primary O. It's got some number of SU2 indices. It's completely symmetric on those. Some number of spin indices. Some number of R symmetry indices. And this is the combination of Q's that kills it. Okay? Simple enough. Okay, you could say this. There are only a couple more of these. This one looks the same. But now it's required that J is 0. There's again a null state, but it's slightly different. Okay, so same kind of formula for the dimension. Sorry, J is 0. But now you need 2 supercharges to annihilate O. And there's only one more, which I'll call B1. And it satisfies this. And it's very easy again to write.
If you don't have time to record all this right now, are we gonna see them in the published work?
Yes, so this is the last one.
Stated? Okay.
This is the last one, sorry.
Thank you.
Right, okay, so you can now the reason I chose 3 dimensions and not say 6 dimensions is because in 6 dimensions the table has 10 entries instead of 4. So, but you again can make it very explicit. Okay, so good. So these are the kinds of operators that exist in 3D n equals 3 field theories. Let me give you, say, a couple examples. Well, I don't know. How comfortable are people with this? Do you want examples of these operators or not? No? No one cares.
Maybe instead a brief remark on in 60, very brief, because I know you're short for time. Is it again 1, 0 examples you have in mind, or 2, 0?
So in 60, for 1, 0 and for 2, 0, you can just make a list of all the possible operators. Okay, the table in 6 dimensions has 10 entries instead of 4, but it's still a relatively short, understandable list.
There are no surprises. It will be a similar list. Okay.
Yeah, no, the structure is always the same. There's always some multiplet with no null state, which satisfies an inequality on its dimension, and then there's a list of possible shortening conditions.
Okay.
And the list is longer because there are more possibilities with spin, but that's it. Okay, so you know these operators are familiar. So you know for example, a conserved current. Some familiar Lagrangian examples. I'll just say a free hypermultiplet turns out to be a B1. A conserved current conserved vector current is also a V1. The energy momentum tensor turns out to be an A1, etc. So all of these possibilities are actually realized in simple field theory. So it's not like that's overkill. They really are all saturated. Okay, so now how do you use this table to set out to accomplish my original goal? So let's examine the condition this was the kind of thing that we wanted to find. What operators O can we find that satisfy this? So this guy here, this O, is some number of Q's acting on a primary. So for instance, so we can study this problem of searching for O's by thinking about what representations the primary is in. So let's say the case where the primary is in an L representation. Okay, well, how can I do this? So I need to make a look. It's important also that this O is required to be a Lorentz scalar because it's something I want to add to the action and preserve Poincare symmetry. So this guy here is Lorentz. Okay, so say the primary is in an L representation. Let's call the primary OP. Now, how can O delta and OP be related? Well, in order to make a deformation, I have to write a Lorentz scalar. And the only way to do it, in general, is to write 6 Q's acting on O. Why 6? 6 is the total number of supersymmetries in this problem. So how am I getting this? So I need to write some O that has the property that it's annihilated by Q's up to total derivatives. Now, this primary has the feature that no non-trivial combination of Q's annihilates it. So in order to get to something that is annihilated, you have to use up all the supercharges. You have to get to the top of that multiplet that I wrote there. Okay. Now, this guy here will, there's a way of contracting these indices to make him a Lorentz scalar. But now you can just easily see that what is the scaling dimension? What is the scaling dimension of this operator that we're trying to add to the Lagrangian? Well, each of these carries scaling dimension 1/2, so this is 3, plus the scaling dimension of O, the primary. And now there's a constraint, there's an inequality here, which tells us this whole thing must be greater than 3. So this operator that we tried to add to the Lagrangian is in fact irrelevant. Okay. And that is the complete illustration of the general method. But now you just have to go through, for each of these cases, and for each of the choices of quantum numbers of the primary, what are the actual things, what are the actual O's that you can find such that you don't end up with something irrelevant. And it's actually a very few number of cases to check, because here you see that if you drive up the quantum numbers of the primary, you drive up the scaling dimension of the primary, which you don't want. You want to have something relevant or marginal. So there's a few cases to check.
Is this the basic trick, take OP and then multiply by number of SUSY charges? Is that...
You mean, are the deformations always top components of
Yes,
multiple?
that's
No,
my
they're not
question.
actually.
Really?
Yeah, so so there are a couple tricky cases where
How can I make correlation with that table when it's not the top one? Should I look at multiplet shortening case or?
Yeah, so it turns out that for some multiplets here, there are scalars in the middle, and Q on them is a total derivative. It's a property of the multiplet that it's true, but it's still something you have to watch out for and look for. So this is a little bit overly simplified, because here I just said, well, it has to be a top component, and that's it.
Can you make a general statement, sweeping statement for the top ones in all cases? Do they share a common property, like being irrelevant, say, or something else?
Well, so it's always true that anything that you take from a long multiplet gives an irrelevant deformation.
Ah, it's a general result.
That's a general result.
Okay.
And then, so this is a kind of version of holomorphy in higher dimensions, right? Long D terms, these are like the generalization of D terms from 40n equals 1, and they're completely irrelevant always. Then there are various kinds of short multiplets, which have some scalars that you can add. And that's a good thing, because it means that since they're short, you can track various properties of them under RG flow. Right? They're protected by supersymmetry in some way. Yeah. Okay, so let me, okay, so you can just continue this, but maybe I won't. I'll just tell you what you find in more detail, say, for 3 dimensions, and then I'll do one physical application. Okay, so what does detailed investigation reveal? So for 3D n equals 3, relevant deformations are so-called real masses. That's the name that they've been given in past literature, which occur in the same multiplet as conserved currents. So if you want to do, so here I'm discussing deformations, relevant deformations, preserving the full 3D n equals 3. And these are the only ones that there are. So they're linked to flavor symmetries. So if you have a theory with no flavor symmetries, it has no relevant deformations, and conversely. Okay, that's the case for 3D n equals 3. This is the kind of result that we can get. Now, what about 3D n equals 4? It's different, in fact. So you have, again, have relevant, okay, in 3D n equals 3, in all these cases, there's no marginal. In all these 3D cases that I'm writing. So now there are relevant defs, which are real masses, but there's another possibility. There's also relevant deformations, so these are, again, in conserved current multiplets. There's also something that I'll call a global mass, which is in the energy momentum tensor multiplet. So this one is kind of interesting, because it means that any 3D n equals 4 theory, whether it has flavor symmetries or not, definitely has an energy momentum tensor. And because of that, it has this relevant deformation, which you can activate without breaking any supersymmetry. This is a kind of universal result. There's this RG flow defined for any 3D n equals 4 theory.
You're not guaranteed a full theoretic realization for all the cases. You could list on group theoretical basis.
So you mean all the operators that I listed?
Yeah.
Yeah. So one of the things, although I did skip this example, but one of the things at least, okay, you can find examples of field theories that realize all of them, but you could ask whether they're all realized in a given fixed field theory. So I mean,
I see.
but they are all realized. So there's no,
In one way or another.
yeah, in one way or another, yeah,
Okay.
you can get them. Right, once you get sufficiently many supercharges, these flavor type deformations go away, and you're left with just these mass terms that are in the energy momentum tensor multiplet. This is kind of interesting. For 3D theories with sufficiently many supercharges, there's guaranteed to be this canonically defined RG flow coming from some operator in the energy momentum tensor multiplet that preserves all the supersymmetry. People have actually studied that in various guises in supergravity before. Okay. Good, so that's all I'll have to say about 3 dimensions. Let me conclude with some remarks about higher dimensions and one physical application. So as I said, in 5D, what do you find? You find relevant deformations are again in real mass terms. These are the only relevant deformations. They're associated with conserved currents. That's it. The marginal don't exist. And as I said before, in 6 dimensions, with even the minimal amount of supersymmetry, neither exist. Okay, so let's conclude with some small applications.
I mean, classically, I could write them down, right? No problem. Classically.
You mean like a cubic term in tensors or something like that, in scalars?
Oops, I had in mind matter coupled. Take tensor multiplet, there will be a dilaton in the multiplet.
Yeah.
I could easily write down.
You mean like the angles
phi
tensor
cube
couple?
or something.
You can write down phi cube, yeah.
So is your statement based on quantum?
Yeah, so unitarity bounds, the things that I'm really using, are really intrinsically quantum.
So you agree that classically I can
Classically, I
write down?
completely agree that you can write them
But
down.
you're not impressed by such a thing, of course. It's
Yeah.
classical. Okay.
Yeah.
All right.
No, I mean, I am impressed by it, but I mean, it's important to note that the method, that using the unitarity bounds, the bounds on delta that you get from the representation theory is an intrinsically quantum thing. There's no analog of that in classical field theory.
Why not? It's representation theory. I can always do representation theory.
But the unitarity bound is something about the norm of a state being positive. That's something that's
And I
formed.
cannot define that classically?
I don't think so. Not that I know
Hmm.
of. Okay, so let's do this physical application.
The thing is here, you can also define more.
Okay, so the physical application I have in mind is the status of super-Yang-Mills in various dimensions. Let's see what we can say just using these very general considerations. So, okay, so first case, 4D. Okay, we all know that super-Yang-Mills with appropriate matter is itself a UV complete CFT. Okay. What about 5 dimensions? Well, 5-dimensional super-Yang-Mills is not even classically scale invariant. Right, 1 over G Yang-Mills squared has dimension of mass, which is 1, not 0. So what can we say about this case? Well, although 5D super-Yang-Mills is not itself a UV CFT, Seiberg has argued in the past, fairly convincingly, that there are UV CFTs in 5D which have an RG flow to 5D super-Yang-Mills of the infrared.
Excuse me, if I couple scalar fields, multiplets to this Yang-Mills, and use Brown-Sticky style, couple it to F squared, I can achieve conformal invariance in that way.
Classically, yeah.
And again, this one of those things will not fly at the quantum level, you're saying?
Yeah. These, well,
Hmm.
I'm about to comment on something like that in a
Okay.
minute. So, okay, anyway, so finally, there's a 5D UV CFT, which can flow to 5D super-Yang-Mills by an NRG flow.
What does that mean exactly? I mean, since you just said that it's not, super-Yang-Mills itself is not a CFT, shouldn't it be flowing to a CFT?
No, why should you flow to a CFT?
Well, okay, you say it's just not a fixed point. I can keep flowing around this.
Endpoints are safety. I thought also like that,
No, this is the famous counterexample to that statement. This is not true in 5 dimensions. This is a counterexample. There are 5D superconformal field theories which have an RG flow that flow to 5D super-Yang-Mills. So this is not a
What are the
CFT.
field, what are the field contents in UV superconformal fields? Theory in 5D.
You mean, how do I write it in terms of a Lagrangian? No one knows how to do
I
that.
mean, the field contents,
no operator content.
I know something, like I know it's set of supersymmetric operators. I don't know a Lagrange, no one knows how to formulate this completely. I mean, okay, I should say that this is probably better viewed as a conjecture.
degree freedom and gauge groups or something.
What so little is known, how can you control the RG flow of it to such a well-defined?
Well, the reason is because the RG flow is driven by this real mass. And that real mass is in a conserved current multiplet, which is a particular short multiplet. It's very protected by supersymmetry. So just matching various BPS quantities fixes this as the unique possible flow if it exists. And so here, this mass term, this mass that I want to add to the action, ends up being equal to 1 over G Yang-Mills in the infrared.
But how much do you need to know about the starting point? This mysterious UV non-Lagrangian thing.
So I mean, there are proposed realizations in terms of branes of these UV-CFTs. There are various things known about conjectured about. There's consistent pictures about their RG flows.
Well, how much of that information do you really need to deduce what you've deduced here?
Not much.
I'd say.
This is known basically just by sort of symmetry matching and moduli space matching. The brane picture gives you some symmetry and moduli space picture already, and you try and match it to the infrared that you get here.
So even if I don't know the theory in 5D, I can know something about this moduli space.
Yeah.
You're saying.
Yeah. So I mean, you know, if you have suppose you have some picture that this thing is realized in terms of branes, when some branes collide, well then you also know what happens when the branes separate. You should get some Yang-Mills degrees of freedom. And so that's what motivates this kind of perspective. I'd be happy to talk more about that in a minute. So let me now conclude with the final column that I'd like to put here, which is 6 dimensions. So this was perhaps a compelling picture. You might think that, well, 60 super Yang-Mills is also not scale invariant. So could I have some UV-CFT which flows in the infrared to 60 super Yang-Mills? Here I'm discussing pure super Yang-Mills for the moment. Can this exist? And we've actually said enough today to prove that this does not exist. If I'm talking about pure super Yang-Mills. So. Why is that? Well, down here, in the pure super Yang-Mills multiplet, there's no scalar. So there's no dilaton. Why is that important? Well, we said that 60 super Yang-Mills does not have explicitly broken RG flows, does not have mass terms, does not have relevant deformations. If you want to break superconformal invariance, you have to do it spontaneously. So you better find, by Goldstone's theorem, a scalar down here. But you don't find it. You can be a little bit more specific and say what you should find. And what you should find is that the Yang-Mills coupling constant in 6 dimensions must be the vev of some field. If you have a UV-CFT that flows spontaneously to 60 super Yang-Mills, you must find couplings of the form that Ergen was mentioning phi f squared. So that the Yang-Mills coupling constant, which is mass-like, can be understood in terms of the vev of a field. So in other words, you can't have this kind of flow if it's not pure, and if there are some scalars coupling to the gauge fields like this. And that's indeed what is realized in examples. So there are UV 6-dimensional SCFTs, which are believed to exist, which flow by going on the moduli space. So they flow spontaneously to coupled tensor vector systems.
This must be 1,0 case, of course.
Yes.
Where you couple tensor multiplet to Yang-Mills, basically.
Yeah.
Because the tensor multiplet provides this scalar.
Exactly.
Right?
Exactly. Yeah. That's exactly right. So these are the kind of general arguments that you can make just using some basic understanding of operators and CFTs. All right. So I guess I'll stop there. Questions?
That's my chance to learn from you the last example, because it's literally related to future of my research program, believe it or not.
I believe in it.
Can you give us a little more information about the last scenario? Is this endpoint, starting point? If I start with 5 square coupling, It's at least classically conformal invariant, right?
Yeah, but I don't think there's, well,
So what's the story here? Is it
you mean
like-
can I prove that you can't quantize it? Is that what you're asking?
No, I want to see where it fits in this flow picture.
Mhm.
Is it coming from someplace as an endpoint or?
It's coming as an endpoint. It comes as an
Of
endpoint.
what exactly? Yeah.
So, okay, so there are believed to exist some 6010 SCFTs. And, okay, again, these are realized, say, in terms of, by, say, branes or singularities.
But no non-Lagrangian.
Yeah,
Okay.
in string theory. And they're non-Lagrangian. Now, if you want to study RG flows of these things, you cannot, because of what I was saying today, you cannot add a mass term to the Lagrangian. But you can get an RG flow. So there is a flow by a spontaneous breaking going on the moduli space. Okay, so there are two branches to moduli spaces in 6010. There are tensor branches and there are Higgs branches. Those could be tensor or Higgs. So let's focus on this case. Then you're going to ask, what do you end up with at the bottom? What you end up with is, in general, some coupled tensor vector system, tensor vector hyper system. But they have to be coupled in such a way that all of the Yang-Mills coupling constants that you find can be interpreted as the Web of a scalar.
Is the endpoint conformal or non-conformal?
You mean as a classical effective action, it's definitely conformal.
Classically it is.
Yeah, as a classical
There
effective
will be
action.
phi f square coupling,
Yeah,
for example.
yeah. Classically, as an effective action, it's definitely conformal. But I wouldn't know how to interpret that beyond a kind of classical effective action statement. So I don't know how to quantize that system, for instance, by itself.
What surprises me is that when you said there's a symmetry break, spontaneous symmetry breaking, you give a web to scalar fields, I thought.
Yeah.
Whereas here, oh, I see, this phi f square, that phi is...
That phi is the dilaton.
dilaton, but
Yeah.
it's not a constant, is it?
Not a constant, right. It cannot be a constant. I'm exactly saying that. It cannot be a constant. 1 over G Yang-Mills cannot be a constant when you get to the infrared. It has to be able to be interpreted as a dynamical field. So you have to be able to shift it around by moving the value of the scalar. So you have to have that phi f squared.
Okay, thank you.
Yeah, so this is indeed the kind of models that you guys are writing down.
Is 5D7's SCFT?
No,
No.
I don't think so. Well,
Classically, it looks like.
well, but have you ever tried to quantize that? I actually have. You get something that looks pretty nonsensical if you try and quantize just pure 5D transiments. You get something that you don't like. Maybe if you add some other fields or something. But if you just talk about pure 5D transiments, it looks pretty bad.
Do we someone has some work to quantize?
I think many people besides myself have done enough work to get it sufficiently confused that they stopped doing it. Which, yeah. I can tell you more about what I thought, but we'll be offline.
Any other questions? All right, it's time to speak again.